Okay. So hi, everybody. I'm Luciano. I'm going to be going over some representative theorems for the single layer ReLU network case, as well as some applications we can then take to classification generalization. So a brief outline is we're going to start with a related problem. And it's going to be this regularized L moment problem. We're going to connect it to some kind of results in convex analysis. Then we're going to introduce a specific framework for total variation representatives. There's some nice work from Untitled et al. As far as that goes for regularized inverse problems. We're going to then use that result to kind of build like a result on top for the case of a single layer network with ReLU activations. And then we're going to take that kind of functional form and then apply it to a Rademacher complexity bound in this function space, right? And then lastly, we're going to kind of see, multi-layer extensions and if we gain any insights of all the results we just seen. So we're going to start with this L moment problem. And so how this works is we have a certain boundary condition we want to satisfy, right? As the name implies, these can be moments of a random variable or whatnot. This is in its very general form. And so I'll go over exactly everything we're seeing here. So we're actually optimizing over a space of measures. And so these measures are called Radon measures. You can just imagine them as measures with some regularity. We're not going to be really going into any of that. So no need to worry. The kind of regularity you can imagine is that these Radon measures are defined on the Borel sets of topology. And if you apply them on one of these open sets or one of these Borel sets, you can kind of approximate from above with open sets on the Borel and approximate from below with compact sets on any open set. Right? So it's a lot of terminology, but I wouldn't really worry about it. You can think of it as measures with some regularity onto them. And so we want to kind of minimize this kind of value, this norm value on the measures, right? And so this norm value we usually refer to as the total variation norm, right? And you can think of it as how much this measure varies along our domain omega here, okay? We're trying to minimize this total variation with respect to some boundary condition. And so to make everything nicer, if this M omega is the space of our Radon measures, we like to consider these phi's as continuous linear functionals on that space, right? So these phi's here lie in the continuous dual of M omega, right? And the nice thing is that this continuous dual does have like a nice integral meaning. And it's this kind of space of continuous functions that vanish at infinity, right? So it's well understood, the subspaces of this space is well understood, and it makes some of the results like easier to kind of extend and use. Right? So this is the very general L moment problem. And so there's some history as far as like representative theory for this problem. So the first kind of characterization or attempt at a characterization of solution was given by Vicky in 1948. And he stated that solutions to regularized L moment problems take the following form, which is this here you see a sum of direct point masses, right? So this was an existence result, not like a full representative, but you can think of it as a representative like theorem. It was almost there. And so this characterization by Vicky was made more precise by Fisher and Jerome in 1975. And what they showed is that measures of these forms are actually extreme points of the solution sets. And so an extreme point is a point on a convex set that no line segment kind of contains it. So you can think of it as the furthest point. If you had a convex solution set, it's kind of some of the furthest points you can have, right? They also extended these representative theorems to the case you had like a modified objective. And so this modified objective, we're going to call a generalized total variation. And so it's something that passes through this measure or maybe just this distribution through this onto transformation. And what they showed is that the kind of form that you see in 2 is kind of modified with the atoms instead of being direct delta masses being this R plus direct delta mass, which R plus is a pseudo inverse that we'll more rigorously define later. Then lastly, a result by Unser et al. Kind of extended this to the unbounded case of the domain, and as well as using weak star continuous linear functionals instead of just continuous linear functionals. This is just something they did. We're not going to really go over any kind of weak star continuity definitions or anything like that, but this is just a result from Unser et al. Right? So this is the history as far as representative problems go for this total variation. And a nice connection is that, so Fisher and Jerome gave a result for the extreme points of the solution, right? But there's a nice consequence from the Crane-Millman theorem that if your topological vector space is X here is nice enough, right? So there's a lot of definitions here, but you can imagine you're just working with a nice vector space here, and you have a compact convex subset of X, right, then this convex subset is exactly the closed hole, the closed convex hole of the extreme points of that convex subset, right? So when we had those extreme points before in this kind of sum format, right, what we're saying here is, so since it is known that the solutions of the total regularization, total variation regularization problem is compact and convex, the solution set is known to be like that. The Fisher-Jerome result tells us that all solutions are really these sums of point masses, right, with these different real value weights. And so that's a really amazing result. We've gone from just a simple existence to a complete characterization of the solution set. And these kind of results are not necessarily unique to total variation regularization. You can imagine different conditions for different optimizations of the form below, for maybe convex G and arbitrary F, and this is something that Boyer et al. Does do. Of course, if you want to get nice results, you either have to assume something about F or about the solution set, right? But those are some of the kind of results we get here. So that's nice, but still kind of removed from maybe what we want to get to, which is the ReLU networks, right? So let's try to keep motivating and see what we can do here. So kind of going off what Fisher and Jerome did, we can imagine some onto linear transformation, and we're going to optimize instead of all the radon spaces, maybe the radon space quotient out some null space of R, right? And so this null, we won't focus too much right now, but we'll make that more rigorous. So we can define this pseudo inverse operator. And again, we might imagine we have solutions completely defined by this Fisher-Jerome result. And so this in generality doesn't tell us much, but if R is carefully crafted, or we have a good idea of what R is and how it behaves, we might be able to get something more nice from this R plus delta X term here, right? So in particular, if R is like a distributional derivative, evaluating R plus delta X is just the same thing as finding some kind of Green's function rho that satisfies this kind of equation, which is the Green's equation. And so we have a lot of literature on Green's functions and these kind of distributional derivative equations. So this is just kind of one example how we can kind of utilize knowledge from very specific onto transformations, what do you call it, to our regularized problem here. So kind of continuing, so R does have to be carefully crafted. It can't just be any kind of transformation. In particular, it's a set of conditions given by Untitled et al. One, that there exists this kind of Green's-like function that when I apply my transformation onto it, I get the point mass instead of at zero. That's the first thing. The second thing is we would like this linear operator to be shift invariant. So one of the things you can imagine is that if I have a Green's-like function and I have the operator being shift invariant, I can take my shift inside of R and all of a sudden generate all kind of point masses for my Green's-like function. So assumption 1 and 2 kind of gives me the result that there's these kind of point masses everywhere on my domain as long as this Green's function exists and my operator is shift invariant. Right? Lastly, and the most you can imagine, maybe it's a strange condition, but we'll kind of get into more why it's not necessarily totally unnatural, is that operator R has a finite dimensional restricted null space. Right? So it's not that its null space unequivocally is finite dimensional, but in a sense that if we consider growth restricted functions, this subspace of the null, or not necessarily subspace, but this smaller part of the null should be finite dimensional, right? So how do we choose? What kind of growth are we looking at? So we want to kind of still consider growth up to our Green's function. This is that very important function we're going to be using. So we are going to first measure the polynomial growth of this Green's function and call that n naught, right? Where we're basing it off this norm here, which this norm kind of, again, quantifies the polynomial growth of the Green's function. And then what we're going to look at is we're going to call NR the growth restricted null space of R, and it looks at all functions where this norm here is less than infinity. Oops. And RF, so R applied to the function, is 0. Right? So this is functions in the null space of R that grow only as fast as our Green's function. Okay. Next, we're going to define just some quick notation. Using that same kind of polynomial growth space, we're going to look at functions that have finite norm, right? So this is also called the native space of R. And so we're going to assume 3 conditions to be met before we get a representative theorem. So the 3 conditions are: 1, R is spline admissible. Spline admissibility was just the few conditions we saw earlier. Our linear measurement operator phi, right, is continuous with respect to the native space. And lastly, we have null recovery. So for any kind of elements in our growth restricted null space, applying our measurement operator R1 on the other, if these are equal, we have equality also in the null, right? So that's also a very important definition, kind of define the null very well. And then lastly, there's this kind of implicit condition here is that, assuming we have a feasible convex compact C in our like RL, which we are measuring our moments in, solutions to the generalized total variation such that we kind of hit this boundary condition, which we give a little more freedom here with the boundary condition. It's not equality, but rather it belongs in the set. We have solutions that take the form like so, right? And these are a complete characterization because these are both extreme points, and you can show that the solution set to here is compact and convex, right? So we get the result from Crane-Milne. And so the two kind of components you see here is one is this sum of Green's functions shifted at different points in your domain, and the other is this null component where P of n is a basis of n of r. Right? So this is nice. So this is kind of like what they call for Untitled, this kind of spline representative for the generalized total variation, right? But okay, what can we do with this, right? So let's revisit that kth distributional derivative with our domain being d equals 1. So we'll just look at the number line. We can find that the growth of our Green's function is polynomial k minus 1, right? And so we can actually compute that directly because you can find that the Green's function is this kind of ReLU to a power, right, divided. And so you can use compute that out here. And kind of associatively, the basis of these null components are going to be these polynomial terms up to power k minus 1, right? And so that's kind of nice. So, these kind of distribution derivatives are really useful. You can imagine functions that represent like this are also fairly useful. We kind of get, again, this ReLU activation we want just for free in this spline, right? There's a few problems here. One of the problems is this is d equals 1. Things get a lot more complicated in higher dimensions if you were to do the spline representative. Another issue here is that generally when we do, we think of these single layer networks or just networks in general, we apply a linear transformation and then ReLU on top of it. And there is no such linear transformation. At most, we're getting kind of like a little shift as far as the xk's go, but no transformation, right? So we'd like to extend this result to include some kind of scaling, so WT transpose scaling, maybe, right? And so one kind of insight that we'll kind of go into more is you can imagine maybe instead of doing total variations on the space of RD, maybe doing total variations on the radon domain, where radon here is something completely different than the radon measure before, right? And so what it is here, so you see the transformation down below, you can imagine it similar to a Fourier transform. We were trying to parameterize maybe some function f of x in terms of some other real value parameters and trying to get some coefficients associated, right? And so in case of the Fourier transform, these are angular frequencies and we get coefficients for each angular frequency. For here, we have two parameters we care about. One is this kind of unit direction and one is this scale parameter, right? And one way you can imagine is that if for Fourier transform, if we're using angular frequencies, in the case of the radon transform, we're going to be using hyperplanes, right? Where the unit direction determines the norm of the hyperplane, and this t is like either the scale of that direction, or you can think of it as distance from that hyperplane, right? From the origin. So it's just another kind of a transformation. But the nice thing is it kind of parameterizes f of x onto these kind of scaling locations, right? And so you can imagine that there might be this little hand wave, but there might be enough stuff here to kind of get us that linear transformation that we want, right? So this is something that Parhi and Nowak showed with they consider the following transformation. So starting from the right to the left, you have this radon transform. You have this kind of ramp filter that we'll go into more that just kind of maintains the surjectiveness of this whole transform. And then lastly, we have those distributional derivatives. And those distributional derivatives are going to give us that kind of ReLU kind of activation that we want there, right? The only change now is that with this radon transform, we're not applying just on x, but rather this W transpose of x, right? Where W transpose is left to be determined. Lastly here, this CD lambda d minus 1 is kind of like, you can imagine a normalization kind of factor. And particularly Parhi and Nowak, so to get this kind of onto this behavior, they want to use the radon inversion formula, right? And so the radon inversion formula only kind of applies to a specific function space, but this function space is dense in our radon space measure. So that's nice. And something that needs to be used is this lambda d minus 1, which is otherwise known as a ramp filter. And the name ramp filter comes from the fact that in Fourier analysis, what a ramp filter is you do a Fourier transform with this specific filter, and you're going to then multiply all your coefficients by this angular frequency term. So that's what it does mathematically, but all we need to know is that it kind of maintains the surjectiveness of this Rn term here. That's what we're going to want to kind of use Unser et al.'s result. So working off Unser et al.'s result, what Parhi and Nowak show is that there's a few little bit difference in the assumptions here, but we'll go into it more. That if our function g is strictly convex, coercive, and lower semi-continuous, if our linear operator is now continuous and surjective, and again, we have no recovery, then there exists solutions, not necessarily a complete characterization, to the optimization there of the form below, right? And so this form here, again, is this sum of ReLU-like functions with this linear transformation and this bias shift, plus some null component, which we're just going to say is a polynomial with degree less than that, right? So it's a very interesting result. A few kind of maybe worries or concerns that we might need to get into is that there's a change in the assumptions. This regularization, this optimization doesn't look exactly the same, but we're going to see that that's not going to matter too much. And then lastly, this polynomial term, this null component, how does that grow? How does that behave? So these are all things we're going to look at. So first, a few differences between theorems 1 and 2. So theorems 1 already had an implicit constraint on this kind of boundary condition on C, right? That we assume that it's compact and convex, right? So equivalently, you could rewrite the optimizations to be kind of accept a similar form. And what happens is that instead of having implicit conditions on this like boundary condition space, we're kind of making that more explicit by assuming conditions on the loss G. So this kind of convexity, coerciveness, lower semi-continuity, kind of just, there's a parallel there. So that's nothing too crazy. There is a new requirement that our measurement operator phi is to be surjective. And that's kind of a consequence of a result that Parhi and Nowak are working off, that when they wanted some kind of onto operator, this measurement kind of operator also had to be surjective, right? So it's a consequence of another paper they're working off of, and the details are pretty in the weeds. But that's where this assumption comes in. And then lastly, we did notice that we kind of degraded from a full representative theorem to maybe a representative-like theorem, which is we have optimized your existence, like an existence form rather than a full characterization of all the optimizers, right? So maybe a little more intuition. So the requirements in G are quite general. So of course, you could kind of rewrite G, you could kind of scale everything out such that you have the optimization of form like so, where loss, the L is some kind of maybe a square error loss. You have this regularization term lambda here. And as far as measurement operators go, those are also can be quite intuitive. You can imagine the case of an ideal sampler operator where you're applying these point masses on our function or on our measure, right? It's evaluating this at every point here. And so in our case, so what we needed for these results to hold is we had to say, okay, the measurement operator had to be continuous, right, and surjective in some cases. And so that is showed in each individual paper. So Unser et al. Did show that for spline admissible R, this does hold for the ideal sampler. And then Parhi and Nowak kind of made that result kind of extended for their case that they care about. So they also show that the ideal sampler is continuous and surjective for these kind of transformations that they're looking at here. Okay, so let's keep further interpreting. So for the case of m equals 2, and that's going to be the case where you have just ReLU activation to no power and to no divider, so it's just a normal ReLU activation. The nice thing is that the polynomial terms are just kind of this skip connection with a bias added. Right, so skip connection is a very popular technique to use in multi-layer networks to kind of propagate the gradient. So nothing kind of disappears and learning can go on nicely. So you kind of get that for free as part of this like norm term regularization, right? And so that's one thing that we see in popular machine learning literature that is kind of reproduced in this representative-like theorem. But another thing is that the actual norm result that we are normalizing against, it can be viewed as a weight decay. So weight decay is this kind of regularizer term that as we're optimizing the loss, we also kind of offset it by, so we add on to the loss, the size of the weights scaled by some lambda, right? And so you can show that for f of theta, so f of this following form, this radon total variation norm kind of simplifies to this kind of result at the optimum. And so we'll go a little bit more into that as far as some equivalence on this weight decay component. So lastly, so we'll get to the more applied part here. So we want to see if we can maybe get some statistical results for like a classification generalization. So what we're going to be doing is we're actually going to be working off a result that we saw in class, where we bounded the risk by this empirical risk plus the Radon marker complexity of a function space plus this high probability term. And then the specific function space we're going to be looking at are going to be the function space of these single layer networks, right? So some assumptions here are kind of similar to class. We assume our loss here is K Lipschitz. It's bounded almost surely. And we're going to define our radon marker complexity as so, which is 2 times the normal radon marker complexity we use. So that's just a normalization thing. And so the kind of function space we're going to be looking at is kind of a bounded weight network class, right? So in particular, when the data is bounded, and that's going to be one of our assumptions later, we're going to consider a function space such that the product of the weights are bounded, and the bias that'll shift there is bounded as well. And so this might seem very restrictive off the outset. So something we're going to do here is hopefully kind of motivate and see that these 2 assumptions on our function class aren't too bad given bounded data, right? So there's going to be 2 lemmas associated with that to show that these are not too restrictive as assumptions. So the first lemma is, considering the ideal sampling scenario, so that was that calligraphy B we saw earlier, the biases is a sparse solution, so that's that single layer solution, satisfy such that each bias is going to be upper bounded by the max 2 norm of the data, right? So one very important thing we're going to be using here is the fact that the not locations, so you can think of this as the bias shift for every possible parameterization of that unit norm, right? It's a little complicated there, but we will kind of gloss over that these not locations are not going to lie outside of the sampling region of a radon domain, right? And that's the case for ideal sampling, and that's something that can be shown, but we're not going to show, right? So in other words, since each of these not locations are parameterized by this unit norm, this unit direction, we can get an upper band of so, considering gamma transpose xi for all these I up to n. And this K here are the different spline locations for each parameterization, right? And so the nice thing is that for kind of a corollary of a result is that this K gamma doesn't tend to infinity. In particular, it's going to be bounded as n minus that null component. So we can imagine upper bounding this K gamma just by n, right? And so since each of these BFKs, these biases are a kind of not location, they're going to be upper bounded by all the parameterizations of these not locations, right? So on the sup of that and on the max of this K gamma, right, we can then further up the upper bound this K gamma by n. And then lastly, we have that variational quality here that we just, this should actually probably be inequality here for 2 norm of our data. So that's how you get the first result. So it's kind of showing that if you have bounded data, then having bounded biases for an ideal sampler is nothing too crazy, right? So that's an okay result there. Next, we have this weight decay equivalence that we'll kind of gloss over and not go into too deeply, but it kind of shows that as long as you have a sparse solution that is also a minimizer, right, the following 2 optimizations are equivalent, right? So we already showed that one of them is just kind of the result of a certain kind of function class, which were these single layer results, but we have to then show that this this weight decay sum is equal to this weight product, right? And so kind of like a sketch that we won't really go into, but you can imagine that as long as your K is small enough to kind of satisfy this constraint that you can both determine the null component and the data term component, the data term component will always be determined without a problem. And so optimizing the whole loss is going to just boil down to minimizing these regularization components, right? So if you show that one regularization could be optimized like the other regularization with no problem, there's this kind of equivalence there that we're not going to change these sparse solutions if we were to swap in one and swap in the other one. So that's kind of like a hand-wavy way of saying it, but Pari and OAK have a more rigorous way of going about that. So now, well, after showing that the function space that we kind of were looking at is not too restrictive, we care about Radon marker complexity bound. So what we say is that this function space with the bounded weights is upper bounded in terms of 2b to the c to the n minus 1, where b was the bound on our weights, c was the bound on our data. And then we have the additive part, which is the Radon marker complexity of the polynomial terms. So there's a little bit of something swept under the rug there as far as we're not expanding that term even further. But we'll get into maybe why that is and how that can be fixed. So without loss of generality, we can kind of shift scalings around in our ReLU activation such that the WKs are equal to 1. So that is also the canonical representation that we're used to as far as the Radon transform it goes, such that our weight product now is just going to be the sum of these absolute BKs. It's less than or equal to B. We're going to be looking at the empirical Radon marker complexity conditioned on the data, right? So fixing the data, and we're just kind of varying our epsilons here with each of these epsilon i's or Radon marker with half probability. Another thing you can note is that the ReLU activation to a power can be represented as the sum of polynomials for the case where m is odd and the case of m is even, right? So you can kind of work this out and see that this will hold. We're going to use the fact that this ReLU is always going to be positive. And so how this works over here for our upper bound is we're first going to use the triangle inequality, and then we're going to use a distributional equality, right? So since our z is fixed in this case, we can have some equality of the marginals in distribution. Okay. So this was the case of we have this kind of upper bound of this this neuron here in terms of this kind of polynomial. But this polynomial is a little more complicated than just being the z. Remember, the z is this kind of scaled xi minus a bias term, right? So we have to go and then actually compute this, or rather upper bound it. So the first thing we're going to do is we're going to do a binomial expansion, and then upper bound which be by the c half here, right? So you get this binomial expansion with this c half up there, and then we're going to rewrite this inner product to the kth power as just a very simple inner product. It's going to be a lot more manageable for us to work with. And so what this x to the k here is this kth order Kronecker product. So you can imagine taking a Kronecker product of a vector over and over again. So if x was d-dimensional, x to the k here is going to be to the k dimension, right? So you can work out the math and see that these are equivalent. So again, yes, since x to the k, w to the k are vectors of size d of k, we can use again the norm variational equality and Jensen's inequality to kind of get this result here. So we got rid of the soup, and we then take out the square root there. And so this term can be evaluated very straightforwardly. So we just expand out the quadratic. These evaluate to 1. These kind of decompose since they're independent, and also evaluate to 0. So we're left with this term here, which again we've assumed is bounded, and we bound as such. And so if you remember before, we had a bias that was m minus 1 minus k. So we have this k component added on top of it. So this becomes constant m minus 1. And then we have this sum of binomial coefficients, which we know is 2 to the n minus 1. So there's some nice simplification that happened right here. Okay, so we're almost there. But lastly, just kind of going over very briefly, you can imagine that for the whole function space, we can kind of upper bound it by this the sum of these vk's absolute value with its complexity of the polynomial term plus this null polynomial, right? Which here we've evaluated the cm minus 1 over this factorial times b, where b was this now the sum from the vk's. This polynomial complexity we still haven't touched, right? And so part of the reason and part of the issue we haven't touched this is that these polynomial terms are not actually affected by a regularizer. So it's not very easy to kind of get a relationship on them or kind of get a bound on them. And so they can very complicatedly depend on, first, one, your data, and two, the actual optimizer you choose here for the optimization problem. And since there is this kind of null space associated with the optimization problem, it's not clear exactly which one you choose. You have to kind of think of each pairs of solutions, and it can be very complicated, right? But this is actually kind of partially addressed in a later work of Barhe and Nowak, where they tried to regularize this component as well. Okay, so when you think of the weight decay problem for these neural networks, these bias terms, these skip connections are also kind of regularized. So there's a disconnect there from what's done in practice and what we'd like, right? So kind of going to the multi-layer extension, what Barhe and Nowak do is they take, again, this Radon total variation, and they tack on this kind of bounded variation regularized part. And so they focus on the case of m equals 2, that's the ReLU case. And so what you see now is that now this F naught is in the regularization, so that bias offset is going to be regularized in the skip connection. And then lastly, the linear part of the skip connection is also going to be regularized. So that's nice. We have some agreement there. We have a new function space associated with all of this. The very nice result is now our k here, the number of neurons, is not adversely affected by our input dimension. So that might not matter for the input dimension, but in the case if you have a very high dimensional latent spaces, you wouldn't want some kind of adverse relationship there. So this kind of addition to the norm kind of takes care of that. And this can be kind of straightforwardly extended to vector valued functions, and it can be composed in a straightforward manner as well. So going really quick, finishing last slide. We kind of showed how recent work for these general total variation optimization problems can kind of be used for these network cases. What we got though are network representative-like theorems, not representative theorems, right? And if we wanted to get a representative theorem, like in the case of Fisher and Unser, we would have to invoke Crane-Millman theorem, which requires knowledge that the solution set is compact and convex, right? One good point in this direction is that Brady's and Caroni, which is some of the work that Parhey and Nowak work off of, showed that if the solution set is convex, then the sparse solutions we saw will be extreme points of this set. Right, so that is almost everything we need there. The difficulty lies in that it's not easy to show that the solution set is compact and convex for this kind of radon measures on the unit ball times the real numbers. Right, the topology on this space is just not as tractable as radon measures on RD. Right, so that's where the main value lies. But if you could somehow get around that with some assumptions, you would then again promote this representative-like theorem to a full-fledged representative theorem. And that's thank you.
Okay, thank you. Any questions? Questions, comments? So maybe I'll have like some comments. Thanks. It was like a lot of material for a 30-minute talk, but no, yeah. So it was a lot to absorb, but it was interesting. So the history that you track, is it? Do they point to this like L-spline problems, or is it something that you like? Yeah, for example, this result that, yeah. So, is it something that they refer to in these papers? The more
right. Yeah. Yeah. Sorry. Yeah. So everyone. So there's a few results I have in the reference I'll show. They all kind of point to different areas, but of the few people that do look at the history, they point to Zoholdecki a lot as this first one, and Fisher and Jerome is kind of crucial in a lot of the results as well.
Is it the famous Fisher, or is it like different Fisher?
I couldn't figure that out. I wanted to know if it was a famous Fisher, but I couldn't figure it out. So
probably like too like recent for the famous Fisher. Okay. So okay. So for example, there's this result that you said like can you go like the next slide? Yeah. So this result, is it recent, or is it?
This one is recent. So this is the Unser et al. Result in 2016.
Oh, okay.
And so this is not very different actually than the Fisher and Jerome result. The two differences with what I mentioned, that now the domain is not bounded, which was useful for Parhey and Nowak, and this doesn't actually have to be continuous. It could be weak start continuous on the native space. What I think is actually one of the greatest contributions to this paper is that the framework they give is very modern. So the Fisher and Jerome papers in the 1975, right? So it works. It's just maybe some of the things are very specific, or it was very specific to splines as well, right? And a very they only looked at certain kind of operators. But the framework they gave was very easy to understand. I could understand it more or less, and it showed that if you satisfy these conditions, you'll get similar results. And I think that is like the great contribution of the paper, which is a very good explainer of how you could produce similar representative theorems if you follow this kind of general framework.
Okay, and then the result of like Parhey and Nowak, does it follow from this, or they have to do something?
They have, so it almost follows almost directly, right? The real difficulty is that radon transform, right? So it's difficult in the part that I don't know too much about function analysis, but there's this issue with the topology of that space I was talking about, this Cartesian product here, right? It's not easily to work on. And so you have to work with a topological tensor. And so Parhey and Nowak don't actually work on that themselves. So that's a work for Brady's and Caroni, where they go really into the weeds on how you would make this work and the new kind of distribution test functions you would need to use, but things do carry over, right? But there is some work to be done there. Yeah.
Okay. And then you mentioned sparse solutions. Is this like something? What does it mean for sparse solutions?
Yes. Sorry, that was I went pretty quickly. So what I guess I meant sparse solution, and that's a word a few authors use as well, is the fact that we're optimizing over this infinite dimensional space. But we can get optimizers that are kind of this linear combination of finitely many terms, right, or finitely many functions.
So anything of this form basically is called sparse solutions. Is that?
Yes. Yes. Yeah.
Okay. And then one question about like the statistical. So the Rademacher complexity, what is the significance of this? It seems like at the best, if you go to the bound that you end up showing. Yeah, so at best, it seems like it's like 1/√n, right?
Mhm.
You ignore it. So it's like the same complexity as if you would. So sorry, can you go back that this, are you fixing rho here? Is that the,
Yes, rho is fixed to that. The form I went pretty quickly. It's like this, right? Except the arguments are the form. They could be of whatever form. Right? So,
okay, so can you go back to the function class then? It's like similar to just, yeah, it's just a linear combination of these with a, so suppose this rho was like the linear function,
mhm.
right? So maybe can you like in your report, can you comment like that would be like a linear class because vk times wk you can absorb into one coefficient, right? So we calculated the Rademacher complexity of that. I think, is there a special case where rho reduces to a linear function? Probably
Kind of
not.
actually, yeah. So it's kind of what I went glossed over pretty quickly, but I showed that this what I did is I took this rho and I upper bounded by this polynomial term, where this
Yeah.
polynomial term was kind of like this here.
Right. What I'm
Uh,
saying is like, just sorry, in this result, it seems like there's no improvement relative to linear classifiers. So it's like
right. Mhm.
that c to the m divided by m factorial. At best, it's like bounded. It seems there's no improvement in terms of, if I increase m, I shouldn't get necessarily better control, right? Is that?
Oh, I see. So if you increase m, there's no better control here. Right. Yeah. The only time we'd get better control is that c was smaller than 1, I guess. That would need some
Or
assumption.
yeah, I would say maybe, is it like c to the m divided by m factorial? Is it going to 0 even if c is bigger than 1? Maybe it's going to 0,
Oh,
or, but okay, but for
yeah.
fixed m, the dependence is not going to change, right? So that's the, if I
Mhm.
fix m, just the kind of result is saying the complexity of this class is similar to the complexity of um, linear functions, basically, on bounded domain. Is
Right.
that
Yeah. And I agree. I think if we plug in here for n equals 2, so that's the simple ReLU case, we get this linear component plus this absolute component, right?
okay?
But what we do here is that we kind of then ignore the absolute component and then go back straight to the linear component with this maybe a loose upper
Okay.
bound. So
Okay.
I think it's exactly what you're saying. Yeah.
Okay. Okay.